Okay, so we are continuing with 12.3. So this is 12.3 continued because I didn't feel good about where I left off. So I want to first start with, we're going to convert parametric equations to rectangular equations. And this is otherwise known as eliminating the parameter. So we're going to eliminate the parameter. So we're going to do a couple of examples because there's two different strategies that you have to use when you're eliminating the parameter, depending on what the parametric equations look like. So whether they have sines and cosines in them or whether they don't have sines and cosines or other trig functions will determine how we proceed. So I'm going to start with the one I think we ended up with last time, and it was linear, if I can find it there. So I think we had x equals 1 minus t was one of our parametric equations, and y is equal to, I think, 1 plus 2t. So those were our parametric equations. So to convert that to just ordinary rectangular, so with the hope of recognizing what the curve is supposed to look like, something familiar. Maybe it's going to be a line or a parabola or a circle or an ellipse or something like that. What we'll do is we'll get t by itself in one of these two equations, whatever looks easiest. Then we'll substitute it into the other one so that we can get rid of the t's and have only x's and y's. So I'm going to pick the t in this one. I think that looks a little easier. I don't have to divide by 2. So I'm going to add the t and subtract the x. So that makes t equal to 1 minus x. And we can substitute that value for t into the other equation. So that makes that into y equals 1 plus 2 times 1 minus x. Now we don't have any more t's in there. So we have successfully eliminated the parameter. And now we just play around with this till hopefully it looks like something we recognize. And I think you can see, because we just have x and y in the first, we're going to get some kind of straight line. So that's going to be 1 plus 2 minus 2x, or in a maybe more familiar form, it's going to be the line y equals negative 2x plus 3. Question?
Is this the same as when it says find the
Cartesian, yeah.
Okay.
So rectangular is the same. That's a synonym for Cartesian equation or Cartesian coordinates. Yep. So those are two different words for the same thing.
Okay.
Yep. Now that's one version of eliminating the parameter. Let me give you a different one that we have sines and cosines in, because then we have a different strategy than we did there. So if we say x is 2 plus, say, 3 cosine t, and y is equal to negative 1, we'll say plus 2 sine of t. Now, the strategy we did when we didn't have trig functions in there was to just get the t by itself. But we don't want to try to take an inverse sine or an inverse cosine. Instead, we remember our favorite trig identity, sine squared plus cosine squared equals 1. And so instead, we will get the cosine t by itself here and substitute that expression in for the cosine and solve for sine of t here and substitute that expression in here, and then we'll play with that and see if we get to something we recognize. So with that in mind, on the first equation, we're going to subtract the 2, and so now we have 3 cosine t is equal to x minus 2. Divide through by the 3, and we're going to get cosine of t is x minus 2 over 3. With me? Okay, so I'm going to hold that for a moment. I'm going to do the same thing with the other one. So we're going to add the 1 to the other side. So 2 sine t is y plus 1. Divide the 2 over and get to sine of t is y plus 1 over 2. Okay? Now we'll plug these expressions into sine squared plus cosine squared is equal to 1. So we're going to get, I'm going to take the x minus 2 over 3 squared plus the y plus 1 over 2 squared, and that's going to equal 1. See how I got to there? So different strategy because of the sine and cosine. Now we can just clean this up and hopefully you'll recognize this. So a fraction squared is the numerator squared over the denominator squared, which would be 9. And we get the numerator squared over the denominator squared. And I don't know, do you recognize that?
Yes.
What's it going to be?
It's an eclipse.
It's a what?
An eclipse.
Ellipse, yeah.
Ellipse.
So it's an ellipse. And it's going to be centered at 2, -1, and radius in the x direction would be 3, and radius in the y direction would be 2. So that's eliminating the parameter.
Do we usually want to leave it in that form? Or
Yeah, I would say leave it here
Okay.
instead of trying to solve for y, which is going to be a mess and not be as recognizable.
And then do you want us to multiply by the greatest common factor of the denominator?
Oh, no. Stop here. Stop here. That's the standard form for an ellipse. So don't go any further than that. I wouldn't leave it here. I would go one more step. Don't leave it here. Go to that. Okay? All right. Well, that's what I want to do with eliminating the parameter. And I want to try to do some of these crazy examples and make sure we can know how to graph this on our graphing calculator. So I'm going to put the problem down, and I'm going to move this camera over to see the screen. That's the best I got for sharing my calculator screen with the video. And I got to check because I tried doing that earlier, it cut off the video. So if that happens, I'll just restart it, but I'm going to have to take a look there. So first, let's say I got a few of these. So let's do straight. What do I have there? Straight horizontal motion. So straight horizontal motion. So the idea is we can do some pretty cool problems with this idea of parametrics and using our graphing calculator. So an ant, let's say an ant walks along a horizontal line, walks along a horizontal line with something. It'll be my own writing. This is embarrassing. With its position, I'm going to say in centimeters, given by negative x equals negative 0.1 times t cubed minus 20t squared plus 110t minus 85. And we're going to say here where 0 is less than or equal to t is less than or equal to 12. And so we're going to try to simulate that on our calculators. Okay, so what we're going to do here, we're going to go to parametric mode, and what I'm going to do is put for t, so the way I give these values is we're going to start with t, which will go from 0 to 12, because we're going to need a Tmin and Tmax on this. We're going to need an Xmin and Xmax, so, and I'll always do them in this order. So after the T values, we'll get the X values, and we'll go from negative 12 to positive 12, and then I'll give you the Y values, and that's going to be from negative 10 to positive 10. Okay? So I'm going to now, here's where it gets challenging. I'm going to try to move this. I'm going to try to, okay, so I'm going to try to keep the camera rolling. That's my challenge. I'm going to try to move it so that it shows the computer screen. So I got it on mine. This is what I want. And so now I'm going to pull up the calculator here. I think that it's still rolling. I think we got success on my end. Okay, so we're going to mode and make sure that we're going to later be in degrees. So if you want to switch it now, a later example is we're going to be in degrees. We don't need it. It doesn't matter on this one. We're going to change from function to parametric mode. And it doesn't matter right now, but later on I'm going to graph it simultaneously rather than sequentially. It won't matter on this problem, but it will for a later example we're going to do. Okay, so given that, we're going to now when we hit y equals, we get all this stuff up there, and yours probably isn't filled in as nicely as mine is, because I think I have preloaded this. So we have x1 is going to be, there's the negative 0.1 times, in parentheses, t cubed minus 20t squared plus 110t minus 85. You can go ahead and put that in there. And what I'm going to put in for y1 is just 5. So that's going to, in our axis, since we're going from negative 10 to 10, it's going to put this line that this ant walks along, and it's going to put it at 5. Now, these things graph, I'll show you first just as it is. So I have put a circle on there, but I'm going to take it without, and just so you can see that it's really hard to follow when it doesn't have that circle on it, because it just goes so fast. You can't really tell what's going on. Now, I have unhighlighted the ones that I don't want to graph yet, but I'm going to move my cursor and hit enter to highlight those. Yours probably is highlighted just because when you type it in, it automatically does that. Okay, we all okay typed in? So we're going to go to our window, and we're going to make this go from 0 to 12. So 0 to 12 for t. There's a t min, t max. The steps should be something around 0.1. So this is balance between speed and smoothness of the curve. So if you make it too big, it's really chunky when it graphs, and if you make it too small, it takes too long to graph. We're going to go from negative 12 to a positive 12 for the x min, x max. And I'm going to leave the scale as 1. Those are the tick marks. And we'll go from negative 10 to positive 10 on the y value, and it's got tick marks of 1. Now, we're going to graph this first, but you're going to see it goes so fast that it's really hard to see. Now, I'm getting some other stuff on there that I didn't want. I got to figure out where it's coming from on mine. Still trying to graph. What did I do? So I have 5. There's something else surviving. I got noise on there. Where's that coming from?
Check out top. Go second one.
Where's all the other parts coming from? Does yours look like that?
No.
I'm not sure where this is coming from here. That shouldn't be there.
It has statistics.
Okay. Yours looks good?
No, mine isn't.
Yeah, it's not looking like, it's not graphing at all?
No.
Ah, here's my stuff that's turned on. Fix that.
That's also, if you check what I'm in
Okay, gonna try it again. There we go. So it's hard to tell what it's doing there. So here's the first fix we can do. And we're gonna do a couple things here. So first, I'm gonna arrow left all the way to the right side and hit enter till you hit the first 0. There's 1, 2, we're there. Don't go one more, you get another 0, but it won't leave a trail. You'll just see a circle go across your screen. Now, when you graph it, it'll slow it down, and you can see where it's changing direction there. Isn't that kind of cool? So there's our ant going back and forth, and he takes off. Okay? Another nice way to do this, so what I've done on the next one, so I'm going to unhighlight this, but you can just, if you drop down, so what I've done here is I'm going to hit enter. So I'm just retyping in that same thing I had for x1, but you can just change the y2 from the 5 that you had to t. And what it's going to do then is it'll scroll it up as it goes, so it doesn't, retrace its steps, but you can see it kind of as time goes. And I would still put the 0 on the end. I think it's kind of nice just to slow things down.
How do you put x1?
So you go to variables, and then go right arrow and down to parametric, and then you can find all the, that's what it's going to look like there. So I'm highlighting my first one and highlighting the second one. So now it's going to look like, so you can see with time where it's going, and here's where it's changing direction. And so time is going from 0 to 12 up the axis there. Okay, and so you can kind of see, it gives you a nice visual of where, it's going to change direction somewhere around, 4 seconds or something like that. And you can trace too, like you did before, in rectangulars. And so now, as you use your right arrow, it moves, it advances with time. So the cursor is responding to the time. So when you do right arrow, it's adding to the time, and then you can see where the x and y coordinates are at each time. And so you kind of see, where do you hit about the largest y value. So somewhere, I guess we want the largest negative x value, and then it's going to turn around and start coming back. Is that okay? Okay, so I'm going to look at a different one then. So we'll change our equation, and oh boy, see if I can do this without disconnecting. So I'm going to look out if you are watching this. So I'm going to try to move the camera so it's back to the board. And I think we're back there, and the camera looks like it's still running. This is success. So we're going to now look at what is that? My handwriting is so small I can't read it anymore. So we're going to simulate projectile motion. So we will simulate projectile motion. So we're going to say distress flare. A distress flare is shot straight up from a ship's bridge. Shot, that would be my phone, straight up from a ship's bridge, 75 feet above the water, with an initial velocity of 76 feet per second. And we are going to first graph the flares height against time. So we're going to go height versus time. This is more like you might have done in an Algebra 2 or a pre-calculus class. And then we will come back, and secondly, we will simultaneously, this will be the second phase, simultaneously graph the flare's height above the water. Okay, so to do this, we're going to go back to refresh our memory about a little bit of differential equations here. We remember that fondly from last year. So we know that because we're talking about feet here, that our acceleration due to gravity is, that would be in metrics. So in feet, it's going to be,
I don't remember.
who could forget, negative 32 feet per second squared. So that's our acceleration. It's a constant. And this, so that's going to be like the second derivative of position, or we're going to call it height. So let's call it h double prime of t. Is that okay? And we know that its initial velocity is 76. So velocity at time 0 is 76, but in terms of h, the velocity is h prime, that kid, yes. H prime of 0. Is that okay? So we know the second derivative, and we know the first derivative. How about the height at time 0?
75.
There you go, at 75 feet from the bridge. That's where the bridge is. Okay? All right, so here's our differential equations. We're going to solve this thing for h. Where do we start? Here. So, we'll integrate both sides with respect to t. I got the right side. The integral of h double prime is going to be h prime. Okay, it's been a while. What's the integral of negative 32 with respect to t?
Negative 32. Oh, plus 8.
Plus c. Oh man, how soon they forget. We'll use our first initial condition. H prime of 0 is 76. That's going to tell us that c is 76. So now we've got h prime of t is negative 32t plus 76. Okay? What next? Okay, we integrate again. I'll keep my same rule. Integral of h prime is h. Integral of negative 32t is going to be
Negative 16 squared.
huh, like you've never missed a beat. Integral of 76 is,
76.
and
Plus
c. A different size c than before. H of 0 is 75 tells us c is 75. Here's our h of t. Negative 16t squared plus 76t plus 75. Okay? So first we're going to graph h, the height, versus time. So we can choose for our window, I think we can go 0 to 6 for t, and then 0 to 6 for the x values, and I think we're going to need 0 to 200 for the y values. Let's see if that does it for us.
Wait, so if we're doing a problem of a test, will those be given to us, or do we have to find those?
Most likely you're going to have to find them. Sorry to tell you. Okay.
And how do we go about that?
Trial and error. Well, you might think, probably trial and error. Now, there may be some other clues. Okay, I want to see, yeah. I can do this without disconnecting my camera. So, got something there. So here we go. Let's see if I'm there. So it's going to be a little seasickness there for the people watching the video. Where did it go? Oh my goodness, we lost it. Huh, I think that'll work. Okay. So let's go to y equals. I'm going to unhighlight the one we just did. And I think we've got, so here is our y1 is equal to, yep, so there's the x is going to be just t, and the height is going to be, here's our parabola, negative 16t squared plus 76t plus 75. Is that okay? You need a minute to get in, or are you guys already there? You guys are quick. So for the window, we're going to try, we said 0 to 6. And we're going to leave our t-step as it is. The x is also going to be 0 to 6 with a scale of 1. And we're going to go 0 to 200. I'm going to pick a tick mark of 100. I don't want to have a fat y-axis. Let's see what that looks like. Get it right. Where is it? I don't think I highlighted it. Let me go back to it. That was the problem. Okay, I want to, this is my third one. Okay, let me try it now. There we go. There's our flare with time. So know that this is time coming across here. This is the height. So, here's where it is at 0, 1 second, 2 second, 3 second, 4 second, and then it's back into the water. Okay, so next what we can do, which is kind of cool, is we can simultaneously graph. So this would be, I don't even know how to describe it. So the time thing is not what you really see. So if you're out there on the water and you're looking and you see this flare going up, it's going straight up and then straight down. And so we're going to graph this as another one. And so my suggestion is that we go and we say, let's call, what do I want? Kind of go back down. So there's the one we just did. Now, let's do, for the x value, we're going to go over to 5.8 because that's going to put it beyond where our flare is going to hit the water. So you're going to see, it's going to hit the water, and then we're going to graph it over to the right of that so it doesn't get in the way of our graph. And we're going to say for the y1, it's just going to be that y3 of t. So I don't want to see this part yet. Okay, so we are going to, this part down here, ignore that for now. So we're just recopying over this height. And it's just going to show the flare going up and then coming back down. That makes sense what we're looking at? And I'm going to put the circles on them because it slows things down a little bit. Otherwise it goes so fast you can hardly see it. We can leave our same window. And if you haven't already, you want to go to simultaneous. Because then we're going to see, then you're going to see both graphs at the same time. The height versus time, and then just the height going up and coming down, which is what you would actually see if you saw this ship way off in the distance. Okay, anyway, here we go. Here's our, that was no fun. Hold on, I ruined it. Come back, let's come to, so I want to highlight that, which it is, and I gotta highlight this one, which I didn't. Okay, try it again. There we go. I should have retyped over there. Okay, one more try. Okay, I'm going to have to type over something to fake out the calculator to make it do it again. So here is our first one. So I'm just going to retype the negative. Then that fools the calculator into thinking it's a whole new thing. And then retype the 5. Now it should do them both from the start. There we go. Oh, what fun. Flash. Okay. Oh, well, I'm having fun. I don't know about you guys. Got one more really tough one. Okay, I'm gonna turn this thing around gently. See if I can go back to the board without stopping the video. Okay, I think we're there. Okay, we're going to hit a baseball here. So we did horizontal motion, we did vertical motion. Now we're going to do it in 2 dimensions here. So we're going to hit a baseball. Okay, so you hit a ball, you hit a ball, and it's 3 feet above the ground. See what kind of power you got here. So we're going to hit that 3 feet above the ground with an initial velocity. So this is now coming off your bat with an initial velocity of 150 feet per second. I'll get this one out of the book. 150 feet per second at an angle of 18 degrees above horizontal. Okay. So, will the ball clear the fence? Will the ball clear a 20-foot fence 400 feet from home plate? Oh, is this not a real life example? I'm going to do this in 9 minutes, guys. This is going to be a challenge. You ready?
Yep.
Okay, so there's the ball, there's the ground, there's the fence. Okay, so this thing is 3 feet above the ground. The trajectory of that ball, when we hit it, is going to be 18 degrees above horizontal. It's going at, what do we say, 150 feet per second. So that's the magnitude of that vector, 150 feet per second. So what we're going to do is we're going to imagine there is no resistance due to air or anything like that. So we have, we have the force acting down, which is gravity, and we have nothing resisting that thing horizontally. So it's going to go forever this way until gravity pushes it down to the ground. And then that's where it's going to hit. That make sense? So in our scheme of things, the x is going to be the component of this force in the horizontal direction. So of that 150 feet per second, the amount that's going in the horizontal direction is going to be what? 150 times the cosine of 18. Excellent. 150 times the cosine of 18 degrees. Now that is going to go forever. So she's going to keep going that way forever. Okay? All right. Then the y, now it is like what we saw before. It's being acted on by gravity. We're going to need its initial velocity is going to end up being the coefficient of t. So to shorten things up, do you remember what the coefficient of t squared is going to be if we start out with acceleration is negative 32 feet per second, and it's going to be a negative 16 t squared. And do you remember what the coefficient of the t was? It's going to be the velocity in the vertical direction. Well, I don't know, so it's going to be 150 times the sine of 18 degrees. Is that what you did, Alan?
No, I was reading the wrong one anyways.
You see where I'm getting that from?
Yeah.
And then plus, what's our initial height? 3. Okay, now, simultaneously, we're going to build the fence. Okay, now our t is going to go from 0 to 3. And we're going to choose our x to go from 0 to 400. We want to see if it makes it out there to 400 feet. And the y value is going to be, let me check, 0 to 80. So to build the fence, so this we're going to put in as our whatever x we're on. We're going to get another X and Y. So we're going to put this out here at 400 feet on the X. And we want, in the course of 3 seconds, for this fence to grow to be 20. So I'm going to take the t divided by the 3 seconds. So as t goes from 0 to 3, it's going to end up going from 0 to 1 times the 20 to get that fence built. Kind of crazy? Oh, this is going to be fun. All right, here we go. All right, hang on, video people. I'm going to try. Do you want to turn it off? We didn't. Okay. And I'm going to try to make the people at home seasick once more. Yeah. There we go. Now we're going to go back to the y equals. I'm going to unhighlight the old ones that I had on here. And I have another one to unhighlight. Then, oh, don't you love it? There it is, the one I want. So our x is going to be 150 cosine of 18 times t, and the y is going to be negative 16 t squared plus 150 sine of 18 times t plus 3. Then we're going to build the fence. So we're going to put it out there 400 feet on the x, 20 times t over 3 for the y. We ready for this? Make sure you're in simultaneous so we can build the fence at the same time. I need a drum roll. Oh, I didn't set the window. Hold on. Stop. Yeah, that doesn't look very interesting. So we got to go from 0 to 3. And we've got to go from 0 to 400. I'm going to make the tick marks be 100. We're going to go from 0 to 80 for the height. And I'm going to make that maybe be 20. Okay, now we're ready. Stage has been set. There's the ball. I think he caught it right there on the warning track. Or maybe it was over his head and it bounced off there. Could be an inside the park home run. Didn't clear the whole fence. Does that make sense? Very good. Okay. This I'm going to cut off. That's good for us.